Hey guys, welcome back to this series on PyTorch. Happy New Year. We are in 2022, so another year. Okay, so I think we are at a pretty decent point in our series where we've discussed how to create layers, how to do stuff, backpropagation, and whatnot. So I thought let's do a code walkthrough of um, of a network. So I was thinking, what network should I choose? Should I do one of the, ResNets, VGGs, or something like that? Instead of that, I decided to do a code walkthrough of the transformer examples because transformers are all the rage right now. So it will be great to just, walk through this code and understand what's going on. Um, so this is an example from PyTorch on transformer, and it's a text example because uh, that's where transformers are used mostly. Give me one sec. Oh, I figure. Right. So that's where transformers are used. But even though that's where they originated from, they have been used extensively in vision as well. And that's the domain I kind of want to focus this series towards, but we'll see. So transformers are basically this um, these networks that use attention mechanism. So the original transformer had an encoder decoder architecture. So this block over here is the encoder, and this block over here is the decoder. Modern transformer networks don't have this distinction. They would either be encoder only or decoder only, because as soon as you add this multi-attention block, you kind of don't need to have this separate encoder decoder architecture. So basically, you feed data all together. So you don't need to feed data in sequentially. So let's say if I pass in a sentence, I don't need to pass in one word and then the next word and then so on. I can just pass it together. And then the attention basically tells you, so let's say I fed the cat. So um, fed and cat would have some correspondence because what am I feeding and who is feeding? So who is feeding is I, and what am I feeding is the cat. So fed is connected to both I and the cat. So that's what attention finds. If you want to learn more about attention, um, look at sequence to sequence models. There are billions of videos on YouTube at this point on it. So so that's what attention finds, and then it adds and normalizes weights in that particular odd fashion. And so that's why attention models work better because they process data together. They're not sequential, so they can be parallelized, and then they model these long um, connectivity, like the long um, connectivity or correlation between two words or objects or things, depending on what you're feeding to the network. So that's why attention transformers are pretty cool. Of course, them being cool makes them very computationally expensive as well. So this is the original encoder decoder transformer. So because this code requires me to delve into the details of transformer, I thought it's a good idea to split this video into two parts. In part one, I will just give you a quick refresher of how transformers work. This by no means is comprehensive, and there are plenty of other videos available on the YouTube that do a much better job than I did. I just want to give you like a quick refresher of, why should you care, or rather, what does this attention mechanism do? Because that's what um, we'll code, or rather, that's the code that we will read. So kind of what you want to know that. So for that, I have Jay Alamar's blog, The Illustrated Transformer. This is probably the best resource if you want to get into transformers, and he also has a video on it, so you can check that out if you want. Okay, so what do transformers do? So in this context of um, or rather in his blog example, he is using them to translate sentences. So translation language doesn't translate 1:1, right? Like let's say I fed the cat. If someone wants to translate, he would have to look at the whole sentence. He cannot translate it, I translate I to whatever language and then fed, then because then grammar wouldn't be correct. So you need to look at the whole sentence at a time. So that's why it's a slightly challenging task. Now, before transformers, we typically had RNN and LSTM-based encoder-decoder networks. So you fed in the statement and you would get some representation, and then you fed that into decoders, and then that would generate the output. That's the old school way of doing it. Now, you could have multiple encoders, and then multiple encoders could give their output to multiple decoders. At each level, I get the same context, and then I generate the output. That's an additional um, level of abstraction. Now you can now then an additional layer of uh, on top of it is if you add some attention. So then came the sequence to sequence attention mechanisms, where there is a kind of like a attention layer between the encoders and the decoder. Given what word the decoder is decoding its attention to the previous the input words, so that would be the attention. So in our transformer, the transformer has this kind of layout where it has a stack of encoders and then a stack of decoders. I feed in my input into the stack of encoder, and then I get out the output sentence. Now each encoder has a feed forward layer and a self attention block. All right, so far so good. And so encoders basically do self attention computation, then do feed forward, and then pass the results of that computation to the decoder block, which has a self attention layer, and on top of that has a cross attention layer, which is an encoder decoder attention, and then a feed forward layer. So that's the difference. There are two kinds of attention, which basically are the same, but for the encoder just has a self attention, while the decoder has an encoder decoder attention. The idea is that while I'm decoding each word, I need to attend to what I have decoded till now, and also the original statement, because that's how we humans also um, understand or like translate things. Okay, so first things first, because you can't feed text blindly into a network, you need to convert text into some kind of a numeric representation of some vector width. So this is called the embedding representation. So there are thousands of ways of doing that, word to vec and so on. So let's say for these three French words, I get some embedding. Again, getting the embeddings, it's a whole different field, so you can get into that rabbit hole as well. So this is how my network will look. For the three words, I would get my self-attention scores, which are Z1, Z2, Z3, and then I'll pass that into the feed-forward network. Good. So, and then because we have these stacks of encoder layers, um, let's say I have thinking machines. So these two words go in, their attention scores get computed, and then I go through the feed-forward layer, and then whatever result I get is passed. It's passed into the decoder. B, it's passed into the next encoder because all these encoders are stacked. So now let's look at self-attention. In this statement, the animal didn't cross the street because it was too tired. Now, when you look at this word it on its own, you don't know what it's related to, right? But when you look at it in the form of a sentence, you know it refers to the animal. So this correlation can be measured by attention. So let's say attention is a score 0 to 1. It has a score of 0.9 with animal and a score of like let's say 0.01 with every other word. All should sum up to 1. So this closer the score is to 1 tells you what it's related to. So it being it, and it has For the word it, animal has a score 0.9. That means it is attending to animal. That's roughly how attention work. So how would we compute this? Like I said this because my brain computed this or figured out this correlation on its own, but the network has to learn this from scratch. So how do we represent that? These folks, the authors of the paper, or rather, the original authors of attention mechanism, which is quite old, um, did basically vector manipulations. So, um, okay, so let's jump into that. Now, they use some database terminology, which is kind of redundant in my opinion, but let's see. So, let's say you have two words in your sentence, okay? Thinking machines. You get their embeddings. So, I get the embedding. Note that embedding dimensions are always the same because you want them to be always the same. Otherwise, you would have to pad them. Okay, so this representation is not enough because now we need three different representations. So from this representation, we generate three different representations: queries, keys, and values. And how do we generate them? Just multiply this with a fully connected layer, have some weight matrix, weight matrix, weight matrix. Okay, so what does query stand for, and what do these stand for? Query stands for what word I am looking at right now. So when you, let's go back to the statement. The animal didn't cross the street, blah, 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 blah. So I was talking about the correspondence between it and animal. Now, which word am I looking at for finding the correspondence? It. So it is my query. Now I will try all the different words to see how closely it is related to. And how do I try this? So every other word is a key. So it is my query because that's the word that I'm looking, that for whose attention I'm seeking. And then every other word is the key. So the is the key, animal, then all are keys, and so on for each and every word. So when I look at animal and I try to search for its correspondence, animal is my query word, and then everything else is the key. So that's how query and key work. Value is just some sort of value associated to each word, just some kind of weight. So um, I don't know, value isn't that important, but I mean for this case it is. So it's just some representation that gives some weight. Okay, now how do we generate the scores? So now what we have done is we have mapped these words into their separate vectors in the query space, in the key space, and the value space. So I have query, key, and value for thinking machine. Now what I will do is I will compute a dot product. So when I look at, when I want to know the attention of, when I'm looking at the word thinking, that's my query. So, and I will take the dot product of um, its query vector with the keys of all the words in my sentence, right? So first I will do q.k1 because I'm looking at itself first, then q1.k2. So first I did q1.k1, q1.k2. Now you would think, why am I looking at myself? That's just for completeness. So that's like the diagonal values in my matrix. Now, of course, a word would have higher attention with itself because the word is itself. So that's why this value seems to be high. And now you look for the next highest value. So that way, so in this query and key space, I do a dot product and I try to see what queries and keys are most closely related. The higher the score, that means they are correlated more. Right, so you get this. Then we perform some kind of a normalization. So in this case, we divide by 8. Why 8? Because we divide by the square root of the dimensionality. It's just mumbo jumbo to make algorithms converge faster, but that's not relevant here. and then you convert it into a score between 0 and 1 by doing softmax. So these are just mathematical mumbo jumbo. What is important is that you are taking the dot product of the query vector with the key vector for all words in the sentence. Same thing for machines. We would do the exact same thing, where for each for Q2 I would compute its dot product with all the K's. So I get attention scores of thinking. I get attention scores for the word machine. So attention would be a 2 by 2 matrix. Attention in general is an n by n matrix, which is symmetric because it tells you how a word is related to the other word. Okay, and now comes the value that I talked about. So once you have the attention scores, you multiply them with value, because value is just a vector that tells you what's the worth of. It's like a representation of the word. So you multiply, or it's value in the value space. So you multiply the attentions and add them. So 0.88 times v1 plus 0.12 times v2, and then you add them, you get the final score. That's all. That's all attention is. You do dot product, you do the softmax, and then you add in value, and that's all. My alarm is ringing, so let me just. Okay, we're back. Yeah, so for each word, I would just get the attention scores, get the softmax scores, and then multiply them by the values, because values is like an embedding. Word value is like a word embedding. So this is my final result after the whole attention process. Now, on its own, it might sound tedious to do it for every word, so you would perform it as a matrix multiplication. So in this case, let's say for all my words, so let's say the two words, I would stack them as a matrix, multiply them. So I would cast it as a matrix multiplication. It's more efficient than doing a for loop. So this is my QKV matrices being generated. For softmax, I also perform this operation and then multiply the value here, and then I get a Z. So that's basically the whole attention mechanism. That's pretty awesome. The good thing is PyTorch gives us, I mean, if we wanted to code from scratch, we can write this layer, but PyTorch has an inbuilt multi-head attention layer, so you don't have to write this from scratch, and that's what we will see in the code. All right. The other thing is that we don't just have one attention layer, we have multiple attention layers. So what is meant by having a we have a multi-headed attention. So what does this multi mean? This multi means that instead of having one Q per word or one QKV per word, we would have multiple of them. So we would have multiple of these matrices generating Q1, Q2, Q3, K1, K2, K3, V1, V2, V3, which will generate Z1, Z2, Z3, which will all work independently, so they can be parallelized, and they will all generate different Z's. The idea is that maybe just one attention mechanism is not sufficient to learn the relation between words. Maybe you need a bunch of them. So, some can understand the verb formation, some can understand nouns in a statement. So, so having this freedom in the network gives increases the representation space of the network. It allows the network to learn different kind of connections. So that's why it's a multi-headed attention, because you have not just your attention heads are the ones that do this computation. Here you can see head 0 is all the 0 subscripted ones, and head 1 is the 1 subscripted one. So you would get, all 0, Z, 0, 1, and so on. Okay, so we get these values, um, the Z's. Finally, what you do is you concatenate all the results from the attention heads, and then you multiply it by a matrix. That's it. So you multiply with a weight matrix. You remember there was a fully connected layer in my each encoder stack, and I get a single Z out. That's all. Get multiple Z's, concatenate them, multiply by a matrix, and get a single Z out. So this is my sequence. This is my embedding, and then I pass it through 8 different attention heads, get 8 different z's, multiply them by a weight vector, I get a single z. That's my encoder block. That's pretty much it for um, for the attention mechanism. Now there is this thing about positional encoding, which, let me see, how do I want to approach this? Um, okay, I will approach it now. The thing is, uh, let's see. Right. Okay. So there's an important concept of positional embedding that I think I will discuss at the end, um, because I don't want to break this chain of thought because what we were doing. So let's go back to the whole attention mechanism. Here we have our encoder, and so we've zoomed out. We're not looking at things so granularly. Um, and then this was what we were talking about, the attention block. Now, these are the two words that are fed in. So this is the block that we looked at. After this, so whatever input comes in also gets routed through. So there's a skip connection where it gets added and normalized. And then I pass it again through a feed forward network where I again add and normalize, um, and get my output out. So that's one whole encoder block. So this is the self attention, which gives me the Z's. Then I take my original input, add and normalize them, pass it through another feed forward layer, and then I add and normalize. Now these normalizations are not batch normalizations, are not L1, L2 normalizations, they are layer normalizations. So let me tell you what layer normalization is. So let's look at this paper. I don't know if this paper has the image. No. There's a pretty nice image somewhere on some blog. Right, this one. Okay, the difference between batch and layer normalization. So let me let me just move it a bit, or let me move myself up. Right, so this is the channel dimension. Let's say we are looking at images. This is the channel dimension. Now this is my batch. That means I have, so each of these slices are my separate images. Each slice is a separate image. So that's my n dimension. Then each has 1, 2, 3, 4, 5, 6 channels. And now I have unrolled um, the h and w dimension as one single dimension. So don't worry about it. So h times w is 1, 2, 3, 4, 5, 6. So the spatials have been combined together and there are like 6 of them. So this is my spatial dimension, this is my channel, and this is batch. So for batch normalization, you take an average for each channel over each batch. So this is what this is the operation that you do to compute your batch norm values. So for this channel, the average, the statistics would be based on this. For the second channel, the statistics would be based on the averages and means and medians and whatnot of the second one, third, fourth, fifth, and sixth, and so on. So that's how batch norm works. But then layer norm works on a per instance basis. So you do the averaging over per instance. So you see, you just look at the first n and you compute the statistics over here, and then the second n you compute the statistics. So at each position in the for each element in the batch, the statistics are different. For each position element, the statistics are different. So that's how layer norm work. I don't know of the motivation of using layer norm off the top of my head, but I'm sure there must be some good justification for it. So yeah, so let's now look at it again. So here are my two words. Notice that There's some another encoding going in, positional encoding, which I will talk about later. And then I have these uh, embedding representation. They go through self-attention and give me Z and Z2. Then I take the original input, do a skip connection, add them, X, the original X plus Z, and then apply layer normalization. So I get, again, whatever I get is Z1, Z2 through the feed forward layer, and then add and normalize again. The whole encoding operation. Sounds complicated, but it's not. And this operation you repeat n number of times. So here we have shown this being repeated twice. Now, the final output, so what is happening? Okay, so this is my encoder block, and I generate some encoding. Now the decoder block also exists over here. Decoder block works sequentially. So decoder generates one word at a time. Encoder takes in all input. Decoder generates one at a time. Because it generates the first word, and then the second word needs to look at the first word, and then also the encoded input, and then it generates the second word. The third word will look at the first two generated words, and then what's the original input. So it also has a self-attention, and these inputs corresponds to, like whatever it has generated before. It has the same add and normalize block, and then it has an encoder decoder attention. So this self-attention is something like a masked self-attention. So what that means is it only looks at things that it has decoded, so only its past predictions, because well, it doesn't have any future predictions. In training, it's masked because you don't want to look at the answer. So it only looks at its previous outputs. So if I say I fed the cat and I'm generating the third word, I will only look at I fed. Now, this encoder decoder attention looks at both what I have generated and also what is the original input, because when you translate, you look at the whole sentences at a time. So that's why this encoder decoder block gets the output of my encoder blocks. So these come in as either queries or keys. So that's I think they come as keys, and the queries come from here, or vice versa. I keep forgetting that, but that's not very important. And then so this output is fed into all the decoders. So this is decoder 1, this is decoder 2, and then finally at the end we have a linear layer and a softmax which generates a word. So I generate one word, feed it back again, generate the second word, feed in the first two words, then generate the third word, feed in the first three words, and so on. That's how this whole transformer thing works. Um, yeah, so let's see. Yes, so that's what I was saying. The encoder decoder, so the encoder decoder attention, the queries come from the word that the queries come from the words that it has decoded, and the keys come from, because you want to see the attention between the input and output sentence, the keys and values come from the encoder. Um, right. So that's pretty much it. Uh, Two more things: the final output layer, and then um, how the loss is computed, and then the position encoding. Okay, so once I get an output of my decoder, um, so there's a lot of math that I'm skipping over, and you should definitely read the original paper, and you should definitely look at other videos, because masked attention has negative infinity values. Um, why is it so, and all those, like, mathematical reasons. You should look at some other videos, but I am just giving you a high level explanation of what's going on, because we don't need to worry about the details, because we will just be using nn dot masked attention. So or sorry, nn dot multi-headed, or whatever it is. Okay, so let's say finally my decoder gives one word output. it decoder only decodes just one word at a time. So that's why one word output, you pass it through a linear layer, and then that generates logits, and then you do softmax, and then you get some word representation, which is just whichever word it is in the index. So I'm here. Now the training is done using any of these probabilistic functions like cross entropy and so on. So that's how you train. But during training step, you feed in the network full sentences. The um, obviously the encoder gets the full sentence always, both in training and inference. The decoder gets a full sentence um, during the training step with the masked attention. So the first, so let's say it's a 5 word sentence that it's predicting. It will get 5 words, and all the five, so it will then predict 5 different words simultaneously, and all the predictions are counted, like whether it got the first word right, whether it got the second word right, third word, fourth word, fifth word. And that's why you have a masked self attention, so that you don't look at the results. That's basically what this is. A lot of these details are kind of redundant. What the only detail that is important is the attention mechanism, or rather the multi-headed attention, because modern networks don't have this encoder decoder architecture. They would only have these encoder blocks, so you don't need to worry about this separate decoder layer. So they only have encoders, or they only have decoders, and that makes life much easier. So that's that. Then comes the issue of positional encoding. Now, why is that important? Let's look at the statement again. The animal didn't cross the street because it was too tired. Now, the network, if I feed this, this is just a bunch of word embeddings, so just a bunch of numbers. Now, there is no order associated to it. The network doesn't know which word came first, which word came last, what's the order of the words, because remember, in English, order of words kind of is important. Network doesn't know that information. So that is the information that we need to specify into it. And that's what positional encoding is. So the idea is, and positional encoding is injected into the network in the beginning. So when I feed the encoder my word embedding, so I inject a positional embedding to each word. And each word has its different positional embedding because they occur in like different places in my sentence. So the way it works is whatever embedding I have, I would add a positional embedding. Positional embedding is just a vector whose word size is the same as the embedding dimensions of my input. Now, now you could just having 1, 2, 3, 4, just numbers wouldn't make sense because numbers are unbounded. So that's why these are vectors. And even for vectors, you need to find a representation that kind of makes sense. So in this representation, this is 1, this means 2, this means 3. So that's the representation I'm talking about. So this is 1, this is 2, this is 3. So that's how this 4-dimensional positional encoding can encode like numbers up to very high in this fashion. So you just add them to the network, and you're off to the races. So the final output is the position embedding combined embedding of your input words. And the way these numbers are generated is by using sine and cosine waves. So basically, so in this example, this is a matrix. First of all, it's just colored. So this is a positional embedding of 20 words. So these are my rows. So these are the position in the rows, and each color indicates what the value is. I don't like these representations. It's like this because it's a sine and cosine wave, but these are some numbers associated, and this is the embedding size. So 512. So position 0 has this value. Position 1 has this value. Position 2 has this value. So these are all different values that once you have a table of these values, it could be anything. Just make sure they're consistent and they don't match, and you can easily use them as positional encoding in your network. So that's pretty much the the transformer network. Now, just to give you a slight idea, let me open up Vision Transformer paper, which is basically a transformer that works on images, and it just has the encoder block. So you can see basically what it does, it breaks up images into patches. So instead of words, now you're feeding some representation of patches, and that's it. And then encoder blocks. Boom, done. And the encoder block is the same what you saw: multi-headed attention, normalization, MLP. Boom, done. None of that additional nonsense. So these, well, you still need the positional embedding, because that's kind of more important here, because which patch in the image it is. So 1, 2, 3, 4, and so on. But yeah, so we don't need complicated architectures like this, but then this is a good enough starting point. Uh, this video went on for longer than I anticipated, but I hope I gave you a quick summary of how transformers work. For more details, read the blog. There are plenty of videos. Read the papers, and yeah, that's pretty much it. In the next video, we'll finally do the code walkthrough. So see you guys next time. Also, please like and subscribe, and I appreciate all the support that I get. And I also have another series on halide, which is slightly more involved, slightly more low level than this PyTorch stuff. But if optimization is of any interest to you, check that out. All right, see you guys next time.